All right, go ahead.
I'm not seeing anything.
You're good. Go ahead.
I'm good? Okay.
Yep.
Hi, everybody. This is Alex, and welcome back to the Astro Imaging channel for Sunday night. I hope you're having a good time. You do realize that it is 9:30 Eastern now. They changed everything around, and it's time for the Astro Imaging channel. I was worried about that all day, that somebody would forget about that. At any rate, here we are. We're going to be going to Debra Ceravolo today, and she's going to be telling us some really interesting things. And let me share some screen with you here, and I will show you some things we've got coming up, some other things that are going to be important. Okay. Oops, that shouldn't be there. That's where I wanted to go. First thing I want to do is go to the calendar, because I want to make sure that you guys understand we've got some good shows coming up. Tonight, Deborah will be telling us about the real colors of Emission Nebulae. They aren't necessarily what we see on our screens when we go on Astrobin and things like that. Then Dave Anderson's going to be here. He'll be here in a few seconds to tell us what's going to happen with his show. Next week, after that, Rory has gotten together with 4 or 5 of the people that are going to be doing Eric Cole's M33 data. We shared that with you a while back, and you can still get a hold of that data, but I don't think you're going to make the show. And then the week after that, we're going to be doing a program about where we include the shows where a number of you people submitted Nebula. That we've got the movie. Arno's made that into a project. Gary M's coming up week after that, and we've got a few other projects coming up, and then we're even scheduling into January already. But we do have some blanks in there, and we've got to get back to working on scheduling people. So if you'd like to volunteer, please send us something by just going to the contact page here and tell us what your name is, what your email address is, and what you'd like to talk about. And we'll be working with you on that. As I said, Rory's putting this together, Eric Cole's M33 data. If you want to work on Eric's files, the link to the data file is still here, and you can go get it. Unfortunately, it's past the time for submission, October 17th. It's past that time, so we aren't really accepting any. But hey, go ahead and send them in, and maybe Rory will be able to show them anyway. And okay, that's enough about the calendar. I mentioned that Dave will be showing up next week. Dave, are you still out there? Can you tell us a little bit about what you're going to be talking about? I'm going to stop sharing so you can do that.
I am. You guys have a lot of amazing people on here that know a lot about astronomy, and I'm going to give you a little comic relief by telling you my basically 4-year journey into astronomy addiction and how it started. And it'll kind of be a mix of my story and also some technical stuff and how I solve some of the technical problems, starting with wondering how you can take a picture with a camera without looking through an eyepiece.
Okay, cool. And I'm not sharing right now. You should be able to just see my old face. I just got back from Nightfall. That's a star party that the Riverside Astronomical Society puts on every year. It's down at a dark sky site. And we had a few people who have presented on the Astro Imaging channel do an imaging workshop there, 4-hour workshop on Saturday. And that included Rory Clark, myself, and Ken Daly, who we've all 3 been on the Astro Imaging channel, and we were fully subscribed. We had as many people as we've ever had at these kinds of things, so we did pretty well. What I guess I wanted to say was, first off, thank you to all of you for coming to that, who did come to it. But I want to tell everybody else, and particularly the guys, Molly and Arno and Eric and Terry and Tolga and Adam and all the people who did I get everybody? All the people who have been doing the workshops on the Astro Imaging channel every Sunday night. A number of people came up to me and thanked us for the work we do. because it's kind of all volunteer. And one guy says, "I have learned everything from you guys." I mean, that's scary, but it kind of makes you feel good inside. So pass the word. Continue to tell people that we have a number of programs that people can look at, go back in the history, that we meet here every Sunday night. And thank you very much for all the nice things you guys said about it while we were at Nightfall this weekend. But that's enough about us. Let's talk about Debra for a while. Debra, who are you, and what did you all? What? Oh! I got to tell you, we got a little bit of an internet problem. Debra is way up in southern Canada and over in BC. I understand she'll tell us more about that. And she lives in a wonderful house. We might even get to see some views of the outside. Beautiful place, beautiful territory. But the internet ain't so hot. So we aren't doing what we usually do. Um, we usually have people live, and they're doing their presentation live right as they do it. Well, Debra and we did not trust her internet, so she's pre-recorded it. So it's going to be a little different. We might, Deborah's there to control what we're doing and stuff like that. So if we have a little bit of a problem, hang with us a little bit. Molly's in charge, so there shouldn't be a very big problem. So, Debra, it's your turn. Tell us who you are and what you're going to talk about, and get Molly working on showing us your program. Okay. Can you go ahead and try it live for a bit here?
Yeah, can you hear me?
Yep, you're coming in fine.
I'm live. Okay. Yeah, I'm not usually used to talking about myself, but I've been interested in astronomy pretty much all my life. And so is my husband, Peter Ceravolo. And we actually run a business here in from our home, and it's an optical business. Peter's a telescope maker, but we make optics mostly for industrial uses. And for the past 2 years, I've really gotten into doing acquisition and processing. I used to do processing about a dozen years ago, but I never did the acquisition myself. And I find that way harder. And my talk is about color. My background is actually graphic designing, so it's probably part of the reason why I'm really into color. And I've always wanted to present my images as being more realistic than playful, if you can, for a better word. So I'll just let Molly go ahead and run it, but I'll be here and we can chat.
Thank you. Go ahead, Molly, take over.
All righty.
Hi, everyone. Welcome to my world on Anarchist Mountain in British Columbia, Canada. We're at about 1,100 meters with a sky quality of around Bortle 3, which makes it really great for capturing faint objects like this soap bubble nebula. But it's not always clear, like this time of the year when the temperatures drop, it gets pretty cloudy. I'm going to show you in a minute. Yes, lots of clouds above, clouds below, and a lot of the time we live in the clouds. So obviously not a lot of imaging going on then. But having a permanent observatory means that I have the luxury of being ready when it does clear. I'm having some fun with some time-lapse photography here. Now on to talking about when it is clear and how I go about getting images and processing emission nebulae. Here I am messing with equipment. A lot of time is spent messing with equipment. But my rule of thumb is that when things are all working together, don't mess with it. It's a lot of work and many things can go wrong, as any astrophotographer would know. My main telescope is a 300 millimeter astrograph here. This is the astrograph here that my husband Peter Ceravolo designed and built. It's a 2700 millimeter setup, and it's sitting on a Paramount ME2. There are two cameras here. There's the S-Big Illuma 694, that's the main imaging camera with a self-guiding filter wheel. And this camera is an S-Big STT 8300, and I use that for guiding and to keep, to keep all the long exposures steady. And I power the cameras and the telescopes with this Eagle 4 Pro computer on the top, and I access it all by remote desktop from my house about 20 feet away, and you can see the Wi-Fi antennas there. I'll just quickly show how I do the acquisition and then move on to talking about color and nebulae. This is the Eagle Manager from the computer that you saw on the top of the telescope. I log into it from inside a nice warm house, and I can turn on the cameras here. Oh, my pointer. So I turn everything on here, and I have USB connections to the mount and the telescope and all the cameras, and I can see the sky quality meter here, and I look at my temperature and the humidity and the dew point, and I just make sure that everything is operational. And while I'm accessing the remote desktop, I can activate the SkyX software. This is the one that comes with the Paramount. You can do many things with this software, but I just use it to find my target and to slew the telescope. And here is a virtual hand paddle for when I want to center my target if the pointing is not perfect. I can also park the telescope at the end of the session. For my main acquisition software, I like to use Maxim DL. It connects the cameras, sets the coolers, and it also has a scheduler here where I can set up the filters and choose which filters I want to use, the exposure times, how many exposures to take, and the file name, and I tell it where to download as well. It also controls the guide camera. I prefer CCD monochrome cameras with separate filters because of the control over color that they have. And they usually are better for noise and high dynamic range than one-shot color cameras or CMOS cameras. But CMOS cameras they seem to be making huge strides in abilities and are probably ahead in popularity, perhaps due to cost. Here I am taking apart a large filter wheel for cleaning that goes on an S-Big STX 16803 full format camera. These are large 50mm Astrodon filters. I have luminance, red, green, and blue, and 3 narrowband filters in there. Narrowband filters, they're a must for capturing the detail in nebulae as they isolate the emissions coming from the objects. Oh yeah, when I got this filter wheel all back together, I noticed that there were 2 little screws left behind, so I had to take it all apart again to see what I did wrong. Also, at this stage, you have to not talk or anything so you don't get droplets on the filters. Just before covering it, I use canned air to blow off any dust. It's really impossible to get the filters perfectly clean, but you do the best you can. And take lots of flat frames to calibrate out any dust that gets on them. There will always be dust getting on them and the telescope mirrors eventually. So it's good to take flats regularly, especially during pollen season. Like here in May, the fir trees go crazy. It's like I have to do flats every night. I also try to get a lot of data and equal amounts of it for each narrowband filter, depending on the object, of course, but I can spend weeks on one target. Narrowband imaging during moony nights and RGB when the moon is gone. In the past, I would blend narrowband images in with RGB images, but I've come to realize that the broadband RGB filters have their place, just not in emission nebulae. Later I will show how broadband RGB filters can overwhelm the delicate detail and misrepresent the actual color of emission nebulae. So I capture RGB data for the stars, and I tend to use luminance filters for galaxies, not emission nebulae. There are many ways to colorize monochrome images, and experimenting with different color palettes it's all part of the fun of image processing. Color in astronomical images has always been somewhat of an obsession of mine for over a decade now. So this talk is obviously about color, but I also think it is important to talk about what emission nebulae are and how color is created inside them. I think these are some of the most beautiful and colorful objects to image and process, and challenging. Even though we astrophotographers are all imaging the same targets from the same location, Earth, there are a great variety of representations of any celestial image. Of course, everyone's situation is different. The gear, the sky quality, the software used, processing experience, and our own personal tastes makes every image unique. There are so many different processing choices that we can make in how we develop our data into a final product. Color is one of those choices. Adam Block once gave a presentation here on the Astro Imaging channel, which I thought was really great. It was called Beauty and the Beholder or something like that. And his message was that each of our images tells a story. Every image is unique and tells a different story from imager to imager. It's all about those choices we make to get to the final product. Choices like what it is we want to portray about the subject, what's physically going on in that part of space. Maybe it presents a certain mood or certain elements that are highlighted. Many decisions were made to get there, including composition, color choices, enhancements, and just different treatments. Our final presentation is personal, so much so that if you came across your own image in a group of other images, or maybe someone tried to pass it off as theirs, you would instantly recognize your own because of the choices you made and the story it tells. My astrophotos also tell a story, usually about color. I'll talk more about this soap bubble image a little later. So in order to talk about colors of nebulae, let's start with what nebulae are and how colors are created in them. I'm sure most of you probably are quite aware of what a nebula is, but I'll just talk briefly as I move into dealing with color palettes and my own spectral palette that I've developed. We can colorize our images any way we want, and that's fine. But I want to better represent the object I am photographing, and in order to do that, I needed to tune into the physics to gain a better understanding of what's happening inside nebulae. So here's a little science lesson. Everywhere throughout our galaxy, floating in space between the stars, there are gigantic cosmic clouds of dust and gas. And the really extreme cold temperatures causes all those atoms in those gases to bind together and form molecules that coalesce into denser regions. And some of these really dense regions of gas, they collapse under their own gravity, and this is where star formation begins. Very hot, brand new stars energize the surrounding gas with ultraviolet light, making the clouds visible at optical wavelengths and giving us amazing things to see and photograph. There are basically three types of nebulae that are technically different from each other. There's the dark nebulae, reflection nebulae, and emission nebulae. And planetary nebulae and supernova remnants are also emission nebulae. So dark nebulae like this Horsehead Nebula are these irregular and familiar shapes made of dust clouds, so dense that they obscure the visible light from behind, making them appear opaque. They are being backlit by bright ionized gases. In the reflection nebula, the Pleiades M45, this type of nebula typically shines with a beautiful blue color because the dust grains in the cloud reflect blue starlight back to us. And this close-up image of the Orion Nebula is an emission nebula. The nebula itself is creating its own light. Note that planetary nebulae, which are still emission nebulae, have a different origin. Planetary nebulae are the expelled atmosphere of a single dying star that's in the process of collapsing. And this Helix Nebula, you can see the star in the center. And the Owl Nebula, you can also see the central star. And this is all its atmosphere that it blew off at its the stage of dying. These are the hottest known stars in the universe, and they create fascinating and beautiful, colorful, and short-lived objects, usually roundish, like planet-shaped, hence its name. But most interestingly, this process will be the fate of our own sun. Many factors influence the color of emission nebulae, including the nature of the chemicals that make up the cloud and the degree to which these gases are being ionized or energized. But I have also learned from experimenting with certain filters
that the expanse of interstellar dust in and around the nebula and along our line of sight can alter the emitted color. And I will show what I mean about that later. Back to the Orion Nebula, this is a close-up of the core. And these hot young stars called the Trapezium cluster are radiating powerful ultraviolet light, causing all the surrounding gases to absorb that really high energy. In simple terms, when the excited atoms settle down, they release that extra energy it absorbed as a photon. That emits at a specific wavelength, and then we correlate that wavelength to a specific color in the visible spectrum. So different gases emit at different wavelengths. By the way, here's an interesting point. Color is a biological concept. Our vision is a product of our evolution here on Earth. The range of the whole spectrum that we see as optical light is optimized for the wavelengths of the radiation that's coming from our own sun. All colors that we see around us and the colors being emitted from space are not real. Well, they are to us because it is us doing the interpreting of what that color is, what that wavelength is. So color is quite a complicated thing. By definition, the visible spectrum is the band of electromagnetic radiation that human eyes can detect. This ranges from wavelengths of approximately 400 to approximately 700 nanometers. Hydrogen is by far the most abundant element in the universe and naturally the dominant gas in Emission Nebulae. But there are other elements that also exist in the interstellar medium like helium, oxygen, sulfur, nitrogen, and others. So here are three of the most prominent elements in most nebulae: oxygen, hydrogen alpha, and sulfur, which also became the most popular filters available for astronomical cameras. When talking about color palettes, you have to talk about the Hubble palette first. So a little history here. The Hubble Space Telescope captured this famous image of the Pillars of Creation in the Eagle Nebula way back in 1995. And the way they colorized it was for a reason. The scientific camera was not equipped with normal red, green, and blue filters, but instead hydrogen alpha, oxygen, and sulfur filters to better capture the structure and detail of the object by isolating the emissions. Now, in typical photography, there are three primary colors, red, green, and blue, that make up a naturally colored image. Also, this is fundamentally how our eyes and brain see normal color, as we're also optically equipped with red, green, and blue sensors that cover the whole visible spectrum. Remember, the universe has no color in itself. Nebulae are emitting electromagnetic waves, but it's our brain in the end that's responsible for giving specific wavelengths colors. So to create a naturally looking photo with three narrowband filters, the Hubble imaging team had to force the narrowband data into the broad RGB channels. This is how the colors of Pillars of Creation came to be. But notice that hydrogen alpha and sulfur are both at the red end of the spectrum. The Pillars was colorized by assigning the sulfur 2 to the red channel, but instead of putting also H alpha in the red channel, it was put in the green channel, and oxygen was put in the blue channel. Since hydrogen alpha was colorized green and is the most abundant gas, the Pillars of Creation was predominantly green, and this combination became known as the Hubble palette. However, the Hubble palette is not the only way to combine color. Those three filters can be creatively rearranged in the RGB color channels to produce different palettes, with a wide variety of colorful and dynamic presentations. The palette names are acronyms with each letter representing the emissions arranged in the order of the red, green, and blue designations. The Hubble palette, now known as SHO, is where sulfur is assigned to the red channel, hydrogen alpha to the green channel, and oxygen to the blue channel. Another less often used palette, often seen in CFHT observatory images, is the HOS. That's hydrogen alpha in the red, oxygen in the green, and sulfur in the blue. Alternately, HSO has a pleasing result with more pinks and purple colors. And the HOO palette portrays a little more natural coloring with hydrogen alpha as red, which is correct, and oxygen as both green and blue, which is correct. The outcomes of these combinations vary depending on the object being imaged and the intensity of the different emissions from that object. Also, one can tweak each color channel to different degrees using different things like contrast manipulation or curves and modifying the palettes. All of these palettes and modified palettes offer interesting ways to explore emission nebulae. Depending on the object and the palettes chosen, different structures in the nebulosity can be highlighted. I do think it's important to mention that creating images from narrowband data using a variety of those palettes can make the star colors in an image look pretty ugly. This is M27 with the HOS palette. It is important to note that stars emit light over the entire continuous spectrum, and the narrowband filters do not allow that whole spectrum through. So they look smaller with weird colors, usually magenta. One solution to achieve properly colored stars in narrowband images is to acquire two sets of data. One taken with RGB filters for the stars, and one taken with narrowband filters for the nebulae. To summarize, you remove the unwanted stars from the narrowband images of nebulae and later replace them with the naturally colored RGB stars. There are image processing tools like StarNet in PixInsight that can effectively remove the stars from the narrowband image while leaving the nebulosity intact. Also, further processing on the starless image allows the freedom to stretch out more detail without worrying about bloating the stars as they are later blended back in. This image I have removed the stars using StarNet in PixInsight prior to adding in the RGB stars. And here are the nicely colored stars. The result is an image with pretty good structural detail and properly colored stars. But how far one takes the stretching of the nebulae is a matter of aesthetics and ethics. I won't demonstrate how to do all of that because there are some really good videos on YouTube. Look up Adam Block for one. I really think good star color is important, so I'll take two sets of data when I'm imaging, RGB when it's dark with no moon, and narrowband data when the moon is out. Narrowband filters only let a sliver of light through, so that makes them really great for moonlit nights and also for places where there's a lot of light pollution. So can we have real or natural color without RGB data or the RGB channels? Remember, real or natural color depends on our brain's interpretation. By real colors, I mean I'm just trying to isolate the wavelengths of whatever is being emitted and integrating that in processing software. It's not perfect by any means, but it's an interesting attempt. 4 color palettes of M27 that I showed earlier, they were put together using this channel combination tool in PixInsight. But the color channels are broad. It's like the actual color of the wavelength is swamped by the whole channel. But the color is diluted or even skewed because of these broad channels. We know we can colorize our images in a multitude of ways to suit our taste, but if we want to represent a more accurate rendition of the colors according to the emission of the nebulae, there is another way. I haven't yet figured that out using PixInsight, but Photoshop makes it easy. I like to use all processing tools at my disposal. I like PixInsight, but Photoshop has its place too. Before I go over to Photoshop, I make sure all the images I am working with have been registered to each other, and I use the star alignment tool here, and then later I use the dynamic crop tool to make sure that they're all lined up together. Then I save each one as a 16-bit TIFF file. Aligning in Photoshop is not easy. It can be done, but it's really not fun. Okay, here I am in Photoshop and I want to colorize my monochrome narrowband images. And I have M27, this is a hydrogen alpha, we've got the oxygen, and I've got the hydrogen beta. I've also brought in the calibrated spectrum for the computer monitor that I got from a professor at the University of San Diego many years ago. And his name is Andrew T. Young, and it shows the wavelengths and the colors attached to those wavelengths. So we're going to be using that in a moment. But the first thing I want to do, I'll go back to the hydrogen alpha, and we have the hydrogen alpha layer here. What we're going to do is we're going to convert it from a grayscale to, we'll get a hold of that in a minute, and to an RGB color, because you can't colorize a grayscale image. And because we want to colorize this layer, we have to go to Layer and New Adjustment Layer, Hue Saturation. We want to use Previous Layer to create clipping mask, so we want to click on that. And what that does is creates this clipping mask with the colors that you can apply to this layer. And to do that, you want to colorize here, and you play with these values. But first, we want to go to the spectrum. No, first we want to go to this spectrum, where I will show you the wavelengths of the different images that I have here for the H alpha 656 nanometers. I'm going to be working with that first. So let's go back to here. We'll bring up the spectrum, and we want to use the eyedropper tool to go to 656, something like there, something about there. Now that changed the color over here in the color picker tool. I'm going to click on that. Now this is got a lot of information in here. We have hue, saturation, and brightness values, which is what we're going to be needing to put in when we colorize the image. And also there's the RGB values, and you can tell that there's a certain element of blue in this hydrogen alpha color. And if you'll also have the lab and CMYK values as well. But we're mostly concerned about the hue is 342, saturation is almost always 100, and brightness is about 57% brightness. Now I'm going to try to remember those numbers, 342, 57 brightness. Let's go back to H alpha, and we're going to 342, I already have it here, but we want 100% saturation. Now we can't say like 60% or whatever, like this is just going to add whiteness to your image. That's the thing that's different about brightness and lightness. Lightness values, it goes from black to white regardless of the saturation. So we're going to be going where it says 0 and down, so 60% of that or 50% of that, well, somewhere around there. So here we got our image for hydrogen alpha, and this should be the proper color. Now if you want to know what it looks like in the regular default setting in Photoshop, that would be 360. So if I change that to 360, you can see how much more red it is. So if you could put it back to 342, and now we have our hydrogen alpha image. And when we're finished with that, I just right click and merge it. Now I've got my image I can play with later. Let's do the same thing for oxygen. Again, we're going to change it from an RGB or grayscale to an RGB. And we want to go to Layer and New Adjustment Layer and Hue Saturation tool. We want to have a clipping mask here. And now let's go to here where it says oxygen is some 501 nanometers or 500 thereabouts. So we want to go here, get our little eyedropper, around 500 down here, and this brings us a value like this. Basically it's 168, 100% saturation, and 67% brightness. So 168. And let's go colorize. Type in 168, 100%. Ooh, that's not 168. I'm working on a tiny little screen here. It's a little tricky. And we're going to do 100% saturation. And that was about a 60%. Something like that. And that would be the color of oxygen. As opposed to green, if you want green, it would be, the value would be 120. Let's just show you what that looks like. There's pure green. So we go back to 168, which this is the oxygen color. Now we're going to merge that down. And the last one, which is hydrogen beta. Let's do it all again, where we're going to change the mode to RGB. And we're going to go to layer, and we want a new adjustment layer. And we want to use saturation tool, clipping mask. Okay. Now, what is hydrogen beta? Well, it says it's 486 nanometers on the spectrum. Let's go to this spectrum here. I picked, what did I say that was? 486. 486, somewhere around there. Let's colorize this. Let's check that color. 190. Not quite 100% saturation, but we can make it anyway. And around 50% brightness. So 190 is the magic number. Let's go back to hydrogen beta, colorize, 100% saturation. And I think I said that was 190, which is bluer. And so let's just check again because I'm doubting myself here. Yeah, 190. Okay. And we want that down. 50%. So now we have, merge down. Now we have the three colors. We've got hydrogen alpha in its proper color, oxygen in its proper color, and hydrogen beta in its proper color. I could also do this with sulfur and so on. So now at this point, I would just layer them all and blend them, or just do a little bit more tweaking with them. That's what we do. You could always go back to, let's see if I go back in the history. Here, let's, instead of like making it, let's just make it some really wacky color. Get any color you want. So that was 190. So there you have it. And this is one way that we can break out of the traditional RGB channels and create any color you want, or one that's really close to the actual emission of the nebula. By the way, if you're interested in learning more about the calibrated spectrum for the monitor, you can go to this address here. All along, I've been mentioning that I've been experimenting with a hydrogen beta filter. Hydrogen alpha is not the only hydrogen emission line in nebulae. Hydrogen possesses many other emission lines that exist throughout the entire electromagnetic spectrum, even beyond the visible. 4 of these lines appear in the visible part of the spectrum and are called the Balmer line series, discovered by Johann Balmer in 1885. Hydrogen alpha is the brightest emission line, of course, and most often used filter in astrophotography. But hydrogen beta is the second brightest hydrogen line, and it's often overlooked in astroimaging, although hydrogen beta filters have long been known to benefit visual astronomy. Hydrogen alpha is about 4 times brighter than hydrogen beta. If hydrogen exists anywhere in space, hydrogen beta is there too, along with all the other lines. H gamma and H delta are very faint and near the violet and are of questionable significance to imaging, but I'm thinking of experimenting with them too. Hydrogen beta is emitting in the blue end of the spectrum, making it a very interesting contribution to an image. However, galactic dust will be the defining factor of its contribution. Dust can attenuate hydrogen beta, much like the reddening of the sky at sunset, where blue light gets scattered by atmospheric molecules near the horizon. Likewise, galactic dust can scatter the fainter blue hydrogen beta light, leaving the red hydrogen alpha to dominate. This is also known as galactic reddening. But where there was less galactic dust in the region, hydrogen beta shines through, causing the nebula to appear more magenta, as you can see here in the bubble nebula. Experimentation needs to be done to determine which objects benefit the most with an H-beta filter, and a lot of data would need to be acquired as the signal is fainter, but interesting results can occur, making the effort worthwhile. So here where there is magenta, we can infer that there's less galactic dust scattering it. the hydrogen beta is shining through. This image is one example using the hydrogen alpha, the oxygen, and hydrogen beta and the spectral palette technique. The colors are different, and I will talk more about how the combinations of colors come through. This is a basic diagram of mixing light and is known as the additive color theory. When all the primary colors like red, green, and blue are added together, the light is white. When there is no color or absence of color, there is black. Our sun is a white light that holds all of the colors that we see. This only shows the primary and the secondary colors, but of course there are many more combinations. For example, a secondary color like yellow, if you mix that with a primary color like red, you will see orange. This is also very simple, but depending on the intensities of the intermingling of different colors, you get a variety. The more colors involved, the lighter the result. I have experimented using an H-beta filter and observed a richness of varying shades of reds and pinks due to the interplay of H-alpha and H-beta and galactic dust. When the blue hydrogen beta mixes with the red hydrogen alpha, you get magenta, just like here blue and red together make magenta. So these emissions also interact with oxygen and create varying shades of pale greens and yellows, like you see in the bubble on the edge of the bubble here, this light yellow color. By understanding how light color theory works, we can begin to appreciate the dynamics of the dust and gases in space. You could simply create a synthetic hydrogen beta, and many astrophotographers do this, by adding H-alpha into the blue channel, but it wouldn't have the same effect as using an actual H-beta filter. This soap bubble nebula is unusual because we're seeing the light yellow of the outer rim of the shell, which is a combination of the oxygen and the hydrogens all intermingling. And the soap bubble itself is attenuating the colors from behind it. And the background has lots of magenta, which means that there's lots of hydrogen beta shining through, so less galactic dust there. This is a really faint object, and I got 45 hours of data to get this. RGB stars have replaced the narrowband stars. And it was taken with my Ceravolo 300 at f9, so it was 2700 millimeter focal length. And the camera was a SBig Illuma 694, which has 4.5 micron pixels, and that gave me an image scale of about 0.4 arc seconds per pixel, and the field of view is about 0.3 degrees, so it's really close up and high resolution. By the way, this kind of imaging is very intensive and requires Zen-like patience and really good guiding. And basically, I threw out about 25 hours of data. So doing this kind of imaging is really hard, but we astro imagers are all really crazy anyway. Finally, here I have M27, the Dumbbell Nebula, mapped with a spectral palette using hydrogen alpha, oxygen, and hydrogen beta. And on the right, I have an RGB image with no narrowband data at all. The blue color in the RGB image is a result of the dominant O3 emission line influencing and amplifying the blue channel. The broadband filter encompasses the O3 line and is dominant in this planetary nebula and most planetaries actually. Both the blue and green filters contain the oxygen line, as you can see here in the diagram. So capturing emission nebulae should really be executed with monochrome cameras and narrowband filters to truly reveal their nature. One-shot color cameras can be much more expedient and a really good choice for certain situations, but they can't compare to monochrome cameras for finesse, high dynamic range, and control over color. At this level of astrophotography, with all the effort required, using broadband filters doesn't make sense, as they can overwhelm the delicate detail and misrepresent the color of emission nebulae. Personally, I think the RGB image is more attractive. I don't really like the colors I've been getting with the spectral palette. It kind of reminds me of the Hubble palette with all that green, but it is what it is, and it's fun to experiment. And here is my latest image, the Crescent Nebula, and it's really pretty wild looking, I think. They have there's the teal oxygen all around, and the yellows along here is the combination of the oxygen and the hydrogens intermingling, and you see some red H alpha here, and you see the H beta in the background. So how we choose to display our celestial photography it's really an individual choice, of course, but there should also be a consideration of the object that we're capturing and a disclosure about how we are representing it. Color is an important and powerful tool, and the colors of the universe can teach us a lot. It's a lot of work doing this kind of astrophotography, especially nebulae, with all the removing of the stars and replacing of the stars and the different narrowband filters and choosing the right colors. And there's many, many steps to get to the final product.
Sometimes when I want to just kick back and relax, I'll process a galaxy or two with LRGB, maybe some H alpha. So that's it, and thanks for listening.
Hi, everybody. We're on a little bit of a time delay here because of the way we had to do things tonight, so that may not come out just as smooth as it should. Now, thank you, Deborah, for doing that, and I think we're all caught up, and we should be on. We should be making sense with the lag on the internet to YouTube. And Eric, have you been monitoring? I asked a question. I know that over there. Let me see if I can get back to it.
Well, I think your question is one I had too, Deborah. If you're looking at two different wavelengths for the hydrogen alpha, but structurally you're looking at the same distribution of hydrogen in the nebula. So what you are probably doing is changing the representation of the hydrogen rather than changing the structure of the distribution of the hydrogen in the nebula. Would that be a fair thing to say?
Yeah, that's fair. And in fact, but there is an extent, there is something about the image itself. I've found that there is a difference in the structure. And like I said, it's got a lot to do with the galactic dust. You would think it would be all identical, but the result is not. And I think I should have showed back and forth on the demo for Photoshop, but you could actually see structural differences from the H alpha and H beta.
And
You go back
also,
to
I guess the parallel question is, you did some stretching on these images in order to balance their emissions, because I think, as you said, the hydrogen alpha just overwhelms it and everything would be green if we assign it green in the RGB palette. So how do you go about stretching the image and keeping your stars under control?
Well, I stretch my images just like I would do any image in PixInsight, and I often remove the stars to stretch the image and then replace the stars like I've mentioned earlier. So pretty much the same as I would do a galaxy. I would stretch. It's not a lot different there.
John asks, how much time is spent gathering RGB star data versus narrowband?
Not as much. I like to get at least an hour for each RGB channel and way more narrowband data. I mean, that soap bubble, for example, I think there was mostly about 50 hours or 45 hours. Most of it was, in fact, narrowband data. So, but I like to go for an hour or two. You know, you don't want to introduce any noise, so you want to always get as much data as possible.
Can I ask, how many clear nights do you have up in BC in a year?
Nothing right now. This is the worst time of the year because it's not cold enough for the clouds to go away, and it's not warm enough for them to stay away, like the big omega highs that we get in the summertime. So pretty much from, I would say, March till about October, maybe 70%. And then, of course, you know, there's always clear nights here and there throughout the winter, and get them when you can.
So you're prepared, whatever, anytime it's clear, you're out there?
Yeah, pretty much. All my friends know me that if it's a clear night, they know where to find me.
Well-
Have you implemented any automation so that, things close, the roof closes automatically or opens automatically and starts when you got to clear, even if you're asleep?
I could do that. I have that capability. I've just been lazy about getting that all set up. I do have a cloud sensor. I could make it completely automated. And through, I think the Eagle, I could control everything through Maxim. I could, but the only things I do is I go out, I open the dome, I take the cap off, and I turn on the mount. Everything else is done from my desktop.
And if a front happens to come through in the middle of the night, does it close up automatically? I mean,
No.
I come from the Pacific Northwest, and I know those fronts come through and, clear at night, and middle of the night it can get rain.
I'm really careful about that. And basically, I'm usually up all night. When it's really, when the season is here, my hours, or Peter's hours too, like both of us, we're up all night. And we close it up in the morning, noon. Or when the sun comes out, we go out and close it all down. But usually there are times when I have gone to bed, but I look at the satellites and I have to be pretty confident to let it go without closing it, because the last thing you want to do is have any moisture coming on that computer for sure, or any of the gear.
There's another question. What do you think about the dual narrowband filters?
I have actually never used them. These are the L enhanced type of filters that people are using for luminance. I'm not sure.
They're generally used on one-shot color cameras so that you can grab two of the narrow bands at the same time.
Usually H alpha and oxygen, I would imagine.
I think it varies from filter to filter. I don't really know enough about them to speculate.
Yes, largely.
Yeah, I've never used them. I basically have always used CCD cameras with filters, mostly because that's what I have.
Mhm.
Usually you use what you have, and I've never experimented with one-shot color cameras, not yet anyway.
Alex, did I miss anything? I was kind of watching the presentation here.
I know everybody was watching the presentation tonight, and all those people who we get a comment rather regularly that we should wait until the end and then ask all the questions, and we did that today because you asked us to. And usually the presenters say, "No, go ahead and ask us when the question comes up." No, there were relatively few questions. Most of the people were just watching. You got them all, Eric.
But it's an interesting idea how to mix those colors.
Yeah. It's just interesting to me is, oh yeah, of course. Why, if you're basically RGB image, but instead of using pure red, pure green, pure blue, you are using the actual color assigned to hydrogen alpha, the actual color assigned to O3 and S2 or whatever you're going to be doing.
Actually, I've done.
Sorry, go ahead.
I'm sorry. I've done the same thing with oxygen. I don't use hydrogen beta, but I've tried to get that blue-green enhancement with the O3. But the other thing that I have to reference a comment from one of our club members. He said, if you were standing right next to these nebula, you wouldn't see any color whatsoever because our eyes are just not sensitive. So the whole idea of what is the real color of that is kind of subjective.
Yeah, well, color is a very interesting thing, and it is subjective. It's different from person to person to some degree. And even from different creatures on the earth, we all see color differently. So can you imagine if you were on a different planet with a different solar radiation, you would see color differently. So it is very subjective.
Well, that's how Superman was able to have X-ray vision.
Yeah. Or if you were a bee.
Yeah, they see in the ultraviolet.
Right, they see different colors. The nebula will look different. Not that we're ever going to get an opinion from a bee, but
Deborah, moving from your photography part, just managing your observatory, Astro Imager wants to know, how do you change your observatory routines when the temperature is below 0 degrees Celsius? What do you do differently when the cold weather comes?
Well, I don't need as much power to cool the camera. I don't do anything different. What I do differently is more in the summertime. We had a huge issue this last summer where we had this heat dome and the temperatures got way past 40 degrees C, and the cameras were struggling, really struggling. So I had to change the temperature base to like -10 or even -5 was the lowest I could go, because the motors were really struggling to keep it cool in that kind of heat. So that, otherwise I don't really do much differently throughout the year.
Okay.
I have that issue here in Australia with my SPIG. It doesn't cool very well, so I've used water cooling in the camera, which drops it probably another 6 degrees, and that helps a great deal.
Yeah, might have to do that next year. See how it goes.
But how many hours of darkness do you get during a typical summer night?
Well, it gets dark around what, 10 o'clock,
Yeah.
10:30 till 4. So about
Okay.
5 hours maybe.
Yeah, that's what, 2-3 hours less than we get down here in Southern California. Damien wants to know, why not use a green filter for the green channel instead of a narrowband emission filter for that color? And this might be a good time to explain what narrowband is versus broadband RGB.
Well, yeah, broadband is about 100 nanometers generally, 80 to 100 nanometers. And so it's letting in a lot of the stuff, other, colors there. Whereas the, like the oxygen is only 3 nanometers or 5
Right.
nanometers.
If we can think back to your the spectral charts you saw as part of your presentation, the green, for instance, goes from blue to yellow, and so you would be getting all of those colors in your green filter, and that's why.
But it's broad. It's very broad, so you're not
Yeah.
really isolating the colors.
And you're not isolating the structures within those colors, because a yellow structure and a
Especially.
green structure would both be represented as the structure green. I mean, or I think I said that right. Both the yellowish, the greenish, and the aqua almost. And besides that, your general broadband RGB filters don't have nice clean cutoffs between the blue and the green. Your typical green filter will actually stretch from the blue all the way up to the red at a lesser degree than the intense green part in the middle of that area. But you can't identify the structures as well, because you've got the red, you've got all 100 nanometer structures all mushing together.
Mhm.
That's all.
Yeah, so it becomes diluted. Yeah. And when
Deborah, how far from Vancouver are you?
it's about a 5-hour drive.
Oh, so you're far enough away, you're getting away from the light dome of.
Yeah, that doesn't affect the sky quality here. I can see the light dome, and it really shows up on wide field astrophotos that I take with my DSLR.
I have
But-
to ask, did you get northern lights in this last eruption last week?
We were pretty clouded out the last one, but the one just before that, we got some. We did. Yeah.
You're not real far from Washington itself, though, right? You're just across the border. I think you can see from there.
Yeah, I could hike there. It's
Yeah. Okay.
close.
Oh, so you're in the eastern part of BC?
Right in the middle of BC on the southern border. It's like right in the middle.
So
It's
you're
the
up in the-
eastern is towards Alberta, but
You're in the
That's another-
Cascades still? I saw there was snow on one of your pictures, so you must be up
Yeah.
in the
it's the
Northern
northern Cascades.
northern Cascades.
Okay. We got any other questions coming in from the YouTubers? I don't see any. I think we got them all.
I think we did, yes.
Okay. Well, thanks everybody for being here tonight, and I hope we can continue to present quality programs like this for you. We do enjoy doing it. We know we're helping people, and we really appreciate your support on the whole that. Okay, so I'm going to be signing off. Deborah, you have anything else to say?
Nope, just clear skies.
Okay. Bye, everybody. Molly, you're still in charge.
All righty.